Hello everyone, good morning. I'll be starting off with a quick overview about what optimization is. And here are some partial steps of a usual forward propagation in which we are having a hypothesis function which is dependent on parameters theta naught, theta 1, which you might consider as the base and bias. And this is a typical linear regression. And then we are just having a usual cost function. And our goal at the end is to minimize this cost function, right? And so now we'll talk about why optimization is generally difficult in deep learning. First of all, in unlike this function right here, in real world, our optimization hypothesis is generally nonlinear, so it's very complex. Here is an example. Here is a universal function, right? So we are just recursing through layers, and which might spike up the inherent complexity of this function. And for instance, I have a function here in which we are just stacking up a couple of sigmoid layers, right? Sigmoid activation function when we forward prop. Now, given this function, right, given the inherent complexity, our cost function is generally has multiple parameters. So it's going to be non-linear, unlike the one here, which is going to be linear because our hypothesis is linear. So our plane is relatively complex, right? Now, for expressing non-convexity, right, we are going to take a short step aside to talk about like the Hessian matrix over how we define convexity in such complex nonlinear cases, right? Now, Hessian matrix, what it is, a quick overview, just a matrix of second order partial derivatives, right? It is nxn, and what that means is that we go to the ith row, how much does the ith vector change when we go to the right? It can be taken as literally. Now, as for the individual entries, right? And now we're going to talk about why did I bring up the Hessian matrix right now, right? Now, as we said, we looked at how the cost function is going to be nonlinear because of inherent multiple parameter dependencies. Now, we know that the state of the optimization algorithms like AdaProp, Adam, right, AdaGrade, these use curvature information, right, to escape the saddle points right here. Because the gradient at this is 0, if we don't use this, our algorithm would stay. We wouldn't be having any weight updation during backpropagation, which is going to be an issue, right? So, and then modern research confirms that saddle points are exponentially more common in higher dimensional spaces, right? Because we don't have simple two-dimensional or 2D functions here, right? It's like a really higher degree polynomial. Now, neural networks are black box, so we cannot really say what exact hypothesis is matching, but then it's safe to assume that it's going to be complex, right? So we are going to be having multiple weights. So like n dimensional, where n is greater than 3, whatever we might say, but it's relatively complex, right? And in such cases, the saddle points are relatively more common, which is more prominent in modern deep learning methods. Now, I'm not going to be talking about how exactly do the optimization algorithms make use of the Hessian matrix, because that involves a bunch of complex mathematics, but they usually use approximation method, right, to approximate the Hessian matrix, because we know that n is going to be large, right? To calculate the whole Hessian matrix for the function is going to be really computationally inefficient and expensive. So they generally approximate the Hessian matrix. They have fancy methods like diagonal approximation, which again I'm not going to be talking about here because of time issues and it's very complex, right? And as for foreshadowing for what's next to come, we are going to be taking a look. Like, let's say this is a classic gradient descent, right? We all know this. So now, if we informally dissect this, right, we are going to have some bottlenecks that my teammates are going to be talking about. For instance, theta is the weight, right? We are going to be talking about some weight initialization issues. If you initialize like at large weights, your convergence, you wouldn't converge, right? You might diverge. And the step size, the learning rate, if you take it like if it's too less, you might never converge. If it's too large, you might overshoot the minimum. And then some gradient initialization. During gradient calculation, if you might have a saturated activation function, you might have vanishing gradients. And then if your gradients are very large, for instance, you might have such problems in the case of ReLUs.